Now, so let's go to, again, website. A second. Don't understand why the browser that is not responding. Okay, now should be okay. Let's see. Okay, good. So Harbour Engineering. And here there is a new exercise. It's application of the CRC formula. Here it is. So this is the text. And let me share the screen. I'm not sure if I shared it. No. Okay. Now I can go here. So you see it refers to coastal engineering, but just and also there is, okay, I think the links are still working. I need to update them. Okay, application of the CRC formula to study the evolution of the coastline. So the geometry of a coastline is described by the coordinates along the x-axis given in the first column of the file, which is this one, which is linked in my website. So you don't need to cut and paste this link. You just click on my website. The second column reports the limiting geometry of the shoreline, which would be attained if a significant erosion occurred. So we will not use this data. It is like a limiting evolution is like the position of a seawall. So if you want to put constraints, it's possible. The coordinates along the y-axis are equally spaced with a step of 150 meters, while the time step is given in this number here in days, which I don't remember if it is 2 minutes or something like that. In R, we can check. The beach is subjected to a wave forcing that is described in this file, linked from my website. And then there is a description of what is in the file. Keep in mind, this file was taken by a public repository. So it's an example of a real file where I removed some of the data which were not useful. Still, there are some data in this file that we will not use. So the first 5 column reports the position of the wave breaker line, not required for performing the simulation, in terms of distance from the corresponding x coordinates of the shoreline. The wave height at the breaker line. This is just an example of what is given to you by these public repositories. So the position of the dominant wave breaker line is usually given by the databases. So wave height at the breaker line, obviously it's dominant wave height. Wavelength at the breaker line, we will not use wavelength, I don't think so, no. The sea bottom depth, the breaker line, we use it. The wave angle alpha with respect to the y-axis, the wave angle, we will see what is the wave angle, how it is expressed. There is a sketch, okay? And then what we need to do is to run a simulation of the beach evolution along 1,000 time steps. Okay, now let's see the sketch. So this is the coastline, and it's given by x and y coordinates. So we get in the file the x coordinates, the y's are equally spaced at 150 meters, okay? And then you don't see here the limiting position, we don't need it. In R we can show it, but here we don't need it. And then the wave angle alpha is measured in this way. So it's not what we defined before, it's not the acute angle between the wave direction and the coastline, which would be alpha 2 here, the blue one. And alpha is given by the angle between the wave direction and the y-axis with orientation landward. So alpha is this one. And this sketch here helps you in finding the angle alpha 2, which is what we need according to our theory, to the CRC formula. And it's not a problem to find it, provided that you know alpha 1, Alpha 1 is the angle between the coastline and the y direction. And this is computable because we know x and y of the coastline, so it is computable, can be computed. Keep in mind that in each step of the coastline, it changes. So here it looks like the coastline is rectilinear, but you will see that in our example, which is a real one, it's not rectilinear. So you have alpha 1 that is continuously changing, and also alpha is continuously changing because the simulation, I don't remember if it is continuously changing. No, maybe that it refers to a constant. We will see, anyway, we will see. Of course, it can change in time, alpha in general. So once that you computed alpha 1 is also reported here in the figure. And then you see that alpha 2 is equal to alpha minus alpha 1. So this is just a sketch that is given to you in order to understand how you have to compute it. Okay, good. And now let's see if there is something more here. No, perfect. Okay, let's go back to the page. And now let's look at this geometry of the shoreline. Let's click here. This is the file whose link was given in the sheet. And you see the two x coordinates, so limiting position on the left and the actual position of the coastline, sorry, limiting position on the right and actual position of the coastline on the left. This file is to be uploaded into R. So let's save it somewhere. And then in RStudio, you can change your working directory, but what we need to do is to save it. So let me save it, coast.txt. I put it in my desktop. Good, and then we can go back. And then there is the wave forcing. The wave forcing, here are the 5 columns, and you see that there is, the time step is 2 minutes. I well remember that it's 2 minutes. And then there is 150, which is the delta y. And then here I have the 5 columns of the data, and I think alpha 1 is actually changing. Let me see what is alpha 1 because I don't remember. I need to go back here and let me look. Wave forcing, I open it in a new tab, and here I go back to the text, which is here. So the 5 columns are the wave angle. Yes, yes. Okay, so this means that given that the wave angle is changing, it means that there is the wave angle that is changing with respect to while moving along the coast. And this is not changing in time, it's just changing in space, and it's supposed to be constant in time. And the wave angle is given with respect to the y direction. So it means that indeed the wave angle is changing, and the alpha is changing, which is fine. I mean, this may happen because of refraction, because of several interaction between the waves. So the same train of waves, when it approaches the coastline, may get shifted in direction in the proximity of the coastline. Okay, and this is our file which we need to save. And let me save it again in the desktop, wave forcing. Very good. And then this 1000 is the length of the simulation, the length of the time steps. Okay. So these changes here are spatial changes and give our initial condition, which we keep for the whole duration of the simulation in terms of wave forcing. And then, of course, the position of the coastline will change in time. Okay. Now, we need, what do we need to do in R? We need to compute all the angles between the wave direction and the coastline. And these angles are to be kept fixed for the whole duration. Which, okay, you may say, I should change the wave angle because of the change of the position of the coastline, but let's neglect this, okay? Let's assume that our wave angle alpha 2 remains constant for the whole simulation. I think this is the assumption that I made, but we will check. And then, once that I computed the wave angle, I can compute I have the wave velocity, so I can compute the sediment transport rate for each cell of the beach. And then I can compute the difference between one cell and the adjacent one and determine whether there is erosion or accretion. And then I move back and forth the coastline at each time step according to erosion or accretion. What we expect is some numerical approximation, which may lead to some unlikely shapes of the coastline. This is why I wanted to keep the simulation short. 1000 time step is not a long simulation. Any time step is 2 minutes, so this is 2000 minutes. It's quite short. If you try to elongate the simulation in time, then you will realize that you end up with some unlikely shapes. In order to minimize the risk of getting unlikely shapes, one thing that we can do, and I suggest that we do it, is to smooth the coastline at each computation. Do you understand what smoothing means? So we are just taking a moving average of the coordinates, but we will see. So this is what we have to do. First thing to do, actually, is reading the files into R. We have an example here. Let me go back from here. We have an example of our file. So what I suggest is, as we did last time, to open it and make a cut and paste between RStudio and Harbour Engineering and the example. So let me open the example. Example of our file. It's downloaded, so just 1 second. It's here. Already opening into RStudio. This is not what I wanted to get, so just 1 second. I close it, because otherwise it's ready. Of course, if we press run, it does it, but this is not what we want to do. Just 1 second, I open it. I think it is already here, so open file. Okay, let me open it with the text editor. Downloads R4. Okay, here it is. And let me just increase the font. Preferences tool. Just 1 second, I don't remember file, edit, view, setting. Sorry? No. Ah, okay, here it is, very good. Okay, so let me open RStudio. Okay, and let me just close this. Don't save, and then file, new file, RScript. Very good. I clear the console. Good, and let me remove also these variables, because otherwise, so let me just, all objects, yes. Okay, environment is empty, perfect. Now I jumped from the file to RStudio, and I make a cut and paste in the script, and then we run, once that we need to check, to make some check, we run it. So first we have the data, what we call fixed data, okay? what we may call fixed data. So it's sediment mass density, 2600. And then the seawater mass density, it's 1025 kilograms per cubic meter. This is a typical value, average value. It depends on the salinity, of course, but this is a typical average value. Gravity, porosity, and here there is a mismatch. Sorry, porosity n equal 0.6, and then I put it to 0.4, and there is a mismatch. K is the parameter to compute the actual sediment transport, and then we have the beach slope. We don't use it here, but there are other formulas that besides CERC that use it. So it is just indicated here because at the beginning there was also another formula that I used, but then I removed it. And then D50, beach grain diameter, which we don't use in CERC. Okay, and this can be just cut and pasted here. I don't think we need to make any comment on this. We can run it. And then we get the variables defined here. Very good. Okay. Now, we will need to make a cycle here to perform the simulation, and two cycles actually, two nested cycles, because one cycle is along the space, and one cycle along time. The cycle along space is needed because at each time step I need to compute sediment transport in different beach cells. So I move in space, I move along the cells, and then I need to move along the time. So let's fix t equals 0. This is not really needed. In R, you don't need to define variables. You just need to define vectors, but okay, that's fine. And we will copy and paste later on. And then there is the input of the data. And therefore, here you see that it starts with by scanning cost.txt. And then we have to make sure of the path. Let me see. Let me. Yes, of course, if you change the name, you need to. Let me see if the path is correct. I don't think so. You see, it doesn't find it, so I need to change the directory, session, set working directory. Choose directory. Okay, and now I got it. Okay. Are you there? Okay, very good. Let's go here. Now, the problem is that cost.txt includes also the second column, which we don't want to use. So I'm not sure whether we already discussed how to select a column in a vector. So basically, if now I look at tier 1, I have 40 numbers. I only need the first column, and these numbers are combined by rows, which means that, let's look at the file so you understand. Desktop. So this is the file. You see that I need only the first column, which is the position of the coastline. And if I look here, you see that it's mixed. I have 426, 380, so I have to pick up only the odd indexes, and therefore 1, 3, 5. How to do that? So what I usually do in these cases is to define a matrix. So basically, I overwrite the variable by creating a matrix from the vector. And I say that the dimension is 2 columns, 20 rows. And then I keep only the first column. And the transformation where I keep only the first column is here. You see? XL coastline is given by the matrix only the first column. And here there is a limiting position, only the second column. So let's make this transformation. Copy. Paste. And then we can move forward by reading the other file. So, first of all, the y. Let's look at wave forcing txt. It's here. You see, the y is just the first row, and there is only one number. So what I can do, what I suggest to do, is here, read only the first row, which is n equal 1. Good. And then now I have to read the t. The t is just one number in the second row. There is also a comment, but the comment is discarded by R when reading. So I need to skip now. I need to take only one number by skipping the first row, because the first row I already got it. So what I suggest to do is, to make another scan of the same file, but I add the argument skip equal 1. And then n equal 1, because it's only one number that I have to read. Okay. This is easy. Now I have to read the number of the delta t, the number of the simulation time step. I just have to read one number, but skip now is equal to, because I have to skip the first 2 rows. Good. Just let me know if something is not clear to you. Okay, let's move forward with wave forcing. I have to skip 3 rows, and then at this point I read all the numbers that remain by taking into account that I have 5 columns. So I copy it. Let me copy also the transformation into the array. 5 columns, 20 numbers. Keep in mind how the file is done. I skip the first 3 rows, and then I read 5 columns, 20 lines. Good. I go here, and I put it here. Now let me just run this from t equals 0 to here. Run. Everything went fine, and I can make a check. The y, for instance, the y is, sorry, the y 150, perfect. The t 120, perfect. And then I can also check PR2 1 comma. Just made a mistake. Just in order to check that everything is fine, if I compare with the phi cost txt, I should find the first column, 37, 44, 52, let's see. Yes, 37, 44, 52, okay. Everything is fine. So it seems that everything was read fine. When you make this computation, make often these checks, because, you know, you have the responsibility of not making mistakes. Of course, we have also to be quick, but we have to learn to make rapid and meaningful checks while working. And you have to be particularly careful of the mistakes that are not evident. So luckily, very often when we make a mistake in uploading the data or etc., we end up with results that are clearly not meaningful. So they are like big mistakes. And this is a fortunate outcome. But in some cases, it may happen that there is something that maybe you don't easily recognize, and you have to be particularly careful to this. And it's really, when you make programs, especially if you make a program that you use several times, just be careful about the subtle differences which are not immediately evident.
I understand that. Here, which you made the metric with all the columns, with the 5 columns. Why it doesn't consider also the first 3 lines above the columns? Like,
because there is a skip here, sorry. When we read PR2, I don't, where is?
Maybe it's in the TXT.
Yeah, but I think I made a mistake here. Just 1 second. Okay, I deleted, for some reason I made a mistake. But when I read PR2, you see that it's scan, wave forcing, skip equal to 3.
So it skips the,
yeah.
It skips the field like this.
Yeah.
Not like this.
No. It's like the skip is the number of lines to be skipped. And if you look at this help of scan, which should appear here on the right, let's see. Don't understand, sorry. Okay. And there is the argument skip equals 0, and you go down, and you see skip. The number of lines of the input file to skip.
Okay.
Okay, and then we have the data. Now let's move forward. And let's put the position and the limiting position of the cost line into vectors, two separate vectors, just for the sake of clarity. It's not really needed, but just for the sake of clarity. And let me copy it. Good.
Sorry, Professor, I think I should know, but it's not clear to me the position of coastline, okay, limit coastline.
Yeah, let's suppose that you have, just 1 second. Oh, it's a good question. Okay, let's suppose that you have a coastline, which is okay, like here, huh? And then let's suppose that you have here a road approaching and passing by here. Of course, you don't want that the road, the safety of the road is undermined. So what you do, you put a symbol here.
Okay, and that is the limit.
Yeah. So basically, you tell the program, eventually, we are not doing it here, but you can do it easily. You tell the program that if you estimate in this cell here, delta xi should be less or equal than a given the limiting position of the coastline. So this is the max erosion that you may have. Which means that if you here compute a sediment transport that is greater than this potential, you have to deliver to the adjacent cell only this amount. And the same may happen with a groin. If you have a groin, you may say, okay, I have a groin here, and therefore here the effect is different. The fact is that if you compute your sediment transport here, so basically this constraint is not precisely the same because I'm not limiting the coastline. But what I say is that this QS here, if it is greater than 0, it's not transported here. So what happens?
You put a limit 0 in that point.
Yes, what happens here then? That if you put this condition, what happens is that here you have an accretion, which is precisely what happens with a groin. Because this one, basically the sediment transport potential is 0. Because you don't, basically even if you compute a high rate, you put it at 0 for the presence of the groin. And therefore everything that comes from here gives an accretion, which is this one. And here you have nothing getting into this, and therefore if you have a sediment transport potential greater than 0, which is likely because otherwise you wouldn't put the groin here, then you get this shape, which is erosion, which is what happens, because with the groins what happens is that you have something like this, and then erosion there. Now, if we look at the code now here, there is a commented line, and it's a test instruction that allows user to upload a straight line coastline with a slope of 45 degrees. This is just for if you want to make some attempts, if you want to see the effect of geometry, etc. And then there is the position of the breaker line, which is PR21. And if you go at the description of what is in the file waveforcing.txt, the first column is position of the breaker line. Let's just 1 second to go back to it. Position of the wave breaker line, which is not needed. We will not use it, but still, let's put it in this vector DLF. And then HB, wave height at the breaker line. LF, wavelength. Some of them are not used. DB, sea bottom depth. And then alpha. Okay, and then let's, these are to be copied. Let's copy it. And just to make sure that everything is okay, let's select the whole script and run it. Okay, no errors. Of course, there are no errors because it's already tested. Otherwise, you would get some errors, of course. Yeah. And then you need to check and look at the error and then go back and make changes. And besides the error, what I suggest is to make these checks, like DLF. Okay, let's see if everything is correct. And you see, okay, this is, I remember that it is like that, HB. Remember that R is case sensitive. And this is, okay, everything is, If you made a mistake, like inverting rows with columns, you would get numbers here that would be not comparable. So you would realize that there is a mix of something that was wrong, okay? Okay, good. And then, let's see, now the y, what is the function cum sum? It's cumulative sum of what? Of the delta y. So I am computing the integral in order to compute the y coordinates. So if you here you make cut and paste and you put it here and you, oops, sorry, and in the script, and you run it, and then you type y, sorry, on the console, you see that it is 150, 300, 450, 600, and so forth, which is okay. Now we have the x and y coordinates, and we can draw a plot of the coastline to see if everything is okay. Let's see if it's here. Yes, it is here, but before then the plot, there is an instruction to keep in memory the original position of the coastline, XLC old, because XLC is going to evolve. And then I want to put, to keep in memory this old position.
Like the y command, y comes soon. It's a repetition with 20 numbers. But how does he know the limit is 3000?
The limit, sorry?
Here, the numbers of y are 150, 300 until 3000.
Yes, because it's 20 repetitions, because I have 20 x coordinates, and, yes, therefore I want 20 y's.
Yeah, but where did we put the limit 3000? To divide 3000 in 20 parts?
Because the y is 150. Oops, sorry.
The y is 150 and was already...
Yeah.
Okay.
Yeah, because if you, in the console, you can see the effect of rep the y20, which is simply, and then if you make...
Okay. Yeah,
okay.
Yes. Because that's the common sum of each before and...
It's the integral, yes. Mm-hmm. Line in red. So let's go here, and then let's run it, and then it should appear a plot in the window here. Now you see coastline, the position of the limiting coastline in red. So let's go here, and then let's run it, and then it should appear a plot in the window here. Now you see coastline and limiting position.
This without changes.
Without changes, without changes. And we will not consider the limiting position here, but just let me, okay, I cannot. I wanted to change this, the lines. You can put a different width if you want. I'm just giving you some examples. Not a graphical parameters, why? Let me see, width, probably, what is wrong here? No. No, it's not width, sorry, it's LWD. This is what I wanted to get. You see that the thickness of the red line is increased. Okay. Now, the next is the spatial cycle. Before the spatial cycle, sorry, let's now, I don't remember what QL is, but if it is defined, it means that later on it is needed. Yes, it is QL. It's the vector of the sediment transport rate. And it is 20 elements long because it's one value per each beach cell. It will be updated at each time step. Now, and then what follows, it's a smoothing of XLC. So you see that what I'm doing here is to substitute any value in the XLC vector, which is the position of the coastline, initial. I substitute it, any value, with the average of the same value plus the next one. And the fourth cycle is extended over 19 numbers. The last one is not averaged. Okay, and this is done in order to smooth the geometry, to minimize the approximation that comes from the fact that I am sampling the coastline with discrete points. This is just something that I decided myself, and because first I tried to run the program without making this smoothing, and the numerical instability was much larger. And then I decided to smooth it, which is fine. When you make numerical computation, you are allowed to introduce assumptions. Of course, you have to be aware of what they imply, and if possible, you can remove them. And you can make experiments later on. Just try to remove this and see what happens, because this is just a smoothing. Okay, and for now, let me copy it and put it into the script. Okay, and look at the fourth cycle. Did we add a look at the, yeah, already. So it's the syntax. Look at the syntax. Okay, and the position of these. Keep in mind that these curly brackets are not strictly needed here because it's only one instruction, and therefore you can avoid them. I just wanted to put them there for clarity, for the sake of clarity. So if you don't make mistakes if you always put them, okay? But with only one line, it's not really needed. Okay, good. And now we have to start our computation, which is, again, to be repeated in space and time. So first, we need to start a fourth cycle running over time. And here you see for I in 1 and delta t. And delta t is the number of time steps. And then there is a curly bracket. And then soon afterwards, there is a second fourth cycle in space. And it's extended for II in 219. Why 2? You will see because sorry?
The first the first cell.
The first cell, you will see that you can't compute it for the reasons that I will explain to you in a while. And because basically I want, in order to compute the angle between the wave and the coastline, I need to refer to two coordinates of the coastline. Otherwise, with one coordinate only, I don't have, the initial, And therefore, I can compute the sediment transport only starting from the second cell, because I use the first cell to compute the direction of the coastline, and then from the second cell, I can compute the sediment transport. But so for now, let's also include the curly bracket, and then let's copy it. Copy and paste. Okay. You see that RStudio is really helpful because it's displacing the instructions so that you realize that you are inside a nested 4 cycle. So you have 2 4 cycles, so it went on 2 times. And this helps you to recognize the instructions that are belonging to each 4 cycle. Okay, now, what is this computation? It's XLC auxiliary, which is, let me make a sketch sheet. So I have my coastline that is done, basically it is a zoom, like this. Okay, good. And then I have the wave angle that is given at each position. So I have a wave angle here, a wave angle here, and a wave angle here. Now, I want to compute the angle between the wave and the coastline, the wave direction and the coastline. Very good. So what I could do is to take these 2 points, compute this angle alpha 2, alpha 1 was called in my sketch, and then I know this angle alpha, and then I can compute alpha 2, which is, let me indicate it here. This one. Actually, what I decided to do is to take 3 points in the computation of the coastline direction. So what I am doing is to compute the angle alpha by taking the difference from this coordinate minus this one. So let me use the red. And then this is my alpha 1. Completely arbitrary. You may say, why did you take this minus this? You could have done an average of the 3. An average slope, like a slope here plus a slope here, and then I take the average. Correct. I decided to do like this because it's a further smoothing. It's a further smoothing because, the position of the coastline is gently changing, and this is just an arbitrary decision. You can try different solutions, okay? But this is what I do, and for this reason I start from the second point, because from the second point I use this wave angle, and as coastline direction I have the difference. I can take the previous one and the next one. But then I need to start from 2 and stop at 19. Is it clear?
Sort of.
I see that you are a bit... because
I understand this whole thing, but...
You don't understand why it changes from 2, it varies from 2 to 19?
Because we wanted the next one.
This is 1.
Okay.
This is 2. This is 3. And let's suppose that this is 20. And this is 19. and this is 80. If I want to compute this difference, I have to stop here. I have to stop at 19. I can start at
because you need the cell after to make the computation.
The cell before and the cell after. So I go from 2 to 19.
But why you decided to do 3 points instead of 2 to be quicker?
No, because I tried with 2, and as I said, this is not an artificial coastline, it is a real one. And I tried with 2, and it was exploding. So
the difference was
yes. And the first thing that I did was to use the rectilinear coastline, and this is easy. If the coastline is rectilinear, even by using the real world data, then you end up with something like this. But it is not, there is not a big difference in the sediment transport between one cell and the next one. But if you have something like this, you understand that there is a huge difference, and then you get suddenly this one that goes much forward and becomes like this. And then it explodes because it increases the difference in angle.
So in that case, you try and have like a mean...
Yes. Because you understand, if, exaggeration, if I just take the difference between 20 and 1, I get a straight line, and I get a very regular shape. And if you get the difference between 2 points is not enough straight, with 3, I thought that it was okay. But you will see, you can really make experiments. It's very easy. It's very easy. And you may resolve it if at the end you make a smoothing. But okay, I decided to do this. And keep in mind that I really looked for something already done, and I couldn't find anything. This is done by me, so I just had to learn by doing. And I saw that with this data, it was probably, I could have reached the same solution if I decreased the wave height, the energy of the waves. And then you decrease the energy of the environment, and the changes are more, are smoothed.
It was like a singularity, no?
Yes.
You had a sort of singularity, so you had to overcome the singularity.
Yes, correct. And then I do it step by step, starting from 2. So I calculate this auxiliary difference between coordinates. I know delta y, and then I can compute alpha 2. Alpha 2 is computed here. As you see that there is XLC aux divided by 2 delta y, y2, because I took the difference between 3 points, and therefore the difference is 2 delta y, is 1 and 2. And then inverse tangent, and then I subtract the alpha, the angle of the wave, and I get directly alpha 2, which is the acute angle between the wave direction and the coastline. And let me see what I copied and what I didn't. So it is a beginning of the 4, so now I need to do this, copy, and paste. I go here, paste. And then I go back again. You see that they are aligned with the second curly bracket, which is fine because it's still not closed. Okay, and now let's see what happens here. Now I am ready to compute the average wave height, because given that I am referring to 3 data points, I need to compute an average wave height. I copy with Control C, and I go here with Control V. Good. Now, there is a test instruction again. You see, allow users to set a specific wave angle with respect to shoreline, and setting alpha 2 equal to half pi should lead to no changes in the shoreline morphology. Why? Because it's across shore, so you don't have, let me see, or maybe it's the long shore. Alpha 2 pi half, I think it is along shore, and then you have no changes because you don't have breakers. Okay, and then here there is the computation of EB, 1/8 rho G HBaux square.
These are the formula we used before.
Yes, and this is wave density per unit horizontal area, energy density per unit horizontal area. And then we multiply times dB. dB is the wave group velocity squared, and then we get the energy flux. Copy. Now, you see that there is a formula that is commented. It's the Campuis formula. We didn't study it. It's very similar. It takes into account the grain diameter, and I think also the slope maybe of the beach. No, the slope no. And we don't use it. We copy the CERC formula, which is what we know, and it's already volumetric because you see that it's divided by rho S minus rho times G times 1 minus N. And then I close the curly bracket, and you see that it goes back automatically. It recognizes that there is a closure. Okay, now let's move forward and see what happens here. There is a comment, QL is positive if alpha 2 is lower than pi half. In this case, the sediment transport is from right to left in the given exercise. It is negative if alpha 2 is greater than pi half, and then the transport is from left to right. This comment is made because you may wonder why you get negative values for sediment transport. It's related to the direction. Now, at this point, we have to compute the difference of sediment transport. Diff is the opposite of cum sum. It's the derivative. Because I need to know the difference from one cell to the next one. And so let's be careful. The resulting vector is counting one less element with respect to QL, of course, because the difference then you decrease. So we computed from 2 to 19, and then we have minus 1 again for the difference. So let me copy it. And then let's go here. Okay, and then we can finally compute for 19 values the delta C. And there is a comment regarding the negative sign here. The negative sign is to ensure coherence. Is if alpha 2 is less than pi half, the sediment rate is positive. Therefore, a negative increment means that there is deposition, and therefore accretion of the beach. So this is why I put a minus there. Because again, if alpha 2 is less than pi half, the sediment rate is positive. I move from the left to the right, and therefore, if there is a negative increment, it means that on the left I have higher sediment transport, on the right I have a lower sediment transport. The increment is negative, and I have accretion. I have deposition and therefore accretion. And therefore, I have a negative difference that should give a positive delta xi. So let me copy this. Sorry?
Because it's the number after minus the number before.
Yes.
So it's the negative. If it's lower.
Yes, it's negative. Yes, correct. It's the difference. So it's yes, it's the second number minus the first. Yes. Okay, and then finally I can compute the new XLC, which is equal to the old XLC plus the yes. And then I can paste this. Very good. And then the last instruction, I can put a line, a new line, without smoothing. So there is not smoothing at the end. So, no, there is a smoothing, sorry. Lowest is a smoothing instruction. And lowest is a smoothing instruction. Let me copy it and then we will see what is lowest. And you see that lowest has an argument, the vector, XLC, the coordinates, and the coordinates, you see that it's y from 1 to 19 plus the y divided by 2, because I put the new coordinate of the line at the midway between the two previous points. And then there is a parameter f. Let's see what is lowest. Scatters plot smoothing. This function performs the computation for the lowest smoother, which uses locally weighted polynomial regression. And you see, f is the smoother span. Larger values give more smoothness. Okay, very good. Now, we should have finished. So let's see what happens if I run everything. So I can select all. Let me run it. And you see the resulting blue line, which doesn't cover everything because I had to reduce the length of the simulation. And it gives a sequence of accretion, erosion, accretion, etc. Now, let's see what happens. Let's start making some experiments. So let's put f 0.1. And I expect a decrease of the smoothness. Okay. You see what happens by just decreasing a little bit the smoothness, because, you know, when there are changes, substantial changes in the wave angle, wave height, then you get a position of the coastline that starts to become spiky, and then the more it becomes spiky, and the more the discontinuity, and therefore you have this result. Conversely, if you put f 0.5, and you run, you get a very smooth configuration. Of course, you may wonder, but what guides me in making this approximation of the numerical computation? And what has to guide you, actually, is your perception of what kind of result you are expecting. So you should look at the data and see what is the reason why you are getting, for instance, a spike that is increasing. So what is the reason? It's a wave angle that is suddenly changing. So the reason is the input data that are, in a way, too discontinuous, or what is the reason? And then you should understand whether this reason actually in the real process provokes a discontinuity or not, provokes something very singular or not. And first you have to look at the current situation. So what is the result of the erosion so far? So, or look at similar configurations. And and you should keep in mind that numerical analysis is just an aid that tells you, if you apply physics, strictly speaking, in a rigorous way, what is the result of physics. But then you have to put this result in the context of the reality. And the smoothness is precisely the fact that why do we smooth? Because we know that the natural environment is smoothed, is not really something that has several singularities, because it's the results from a situation that is more or less in equilibrium. And if it is more or less in equilibrium, you don't have singularities, because the singularities are removed in an equilibrium situation. Of course, you don't have to smooth too much. And another thing that you should do is to try different tests. And another curious thing is, let's try to see what happens if from 2000 I pass to 10,000 number of time steps. Where is the time step? Let me see. I think it is in the 4. N delta t is N delta t, yeah. So let's change N delta t. So let's put here an instruction, N delta t equal 10,000. And see what happens. Let's keep this high smoothing. Oh, you see that it's, even if I smooth it a lot,
I write the number. No, I copy it. No. 10. 10, 12, 10.
but this result that I see here may be not completely meaningless, because on the left I don't have a boundary condition. I put the entrance of sediment transport is 0. And it may be, what is telling me this simulation? That it tends to assume an horizontal shape with respect to this reference system, the beach, which may be reasonable. May be reasonable because maybe that the wave angle, we should look at the wave angle, what is the value of the wave angle. But if the wave angle is such that essentially here the sand is removed from the left and brought to the right. And the reason may be that I don't have any entrance from the left, so this may be the result of this limiting situation, or whatever. I think, but I think it's not unreasonable. And if here I put f 0.3, let's see what happens. It is, but it is not really meaningless, and I don't think it is. I was more happy with the previous situation. I think here a smoothing is actually needed, and then if you put here, if you almost remove any smoothing, you see that it becomes unreasonable. Yeah, it is unlikely. I mean, it is not.
And how you set the limits, the boundaries? You set them at 0.
Yes, we don't have any, yeah, it's 0. I mean, the sediment transport that is computed on the left and on the right is 0. I think we should...
Sorry, Professor, where we can find this on the code?
On the code is the computation of QL. So if you put here, you may put here, cat L fill equal true. The problem is that it doesn't stop, so I don't remember how to pause the program. What we could see is, and then if II equal to 100, for instance, and then I would like a pause. I don't remember. Let's see. Pause our project. I think it is pause, but I don't remember. Pause function. because the pause is pause seconds. Very good. So let's pause 5 or 10 seconds. Which means, but no, okay, so I think we could do like this, because this pause is only one time. So I equal to, let's see. We could make it, okay. I could make it pausing at each time step. Let's see what happens. Run. Now let me clear the console first. Run. Pause. It's not found. Let's see, because I thought it was pause. I don't understand what I did incorrect. Let me see.
Okay.
Pause 10.
Okay, so because you initialized the QL of 20 spaces, all zeros, and then you substituted from 2 to 19.
Yes.
You kept 0, 0 at the 3.
Yes, and you could set a value different from 0, but in order to set this value, I wanted to understand the order of magnitude, and I don't understand why pause. Okay, let's do like this. Let's do like this. Just 1 second. Okay. I'm just printing the value at 100 time step. So now it should work, because I don't know why, but the pause function is not working. And what is here? Lines unexpected. So let me just check. I don't understand why. Lines, this should be okay. I think I made for sure a mistake here. Let me see where is the cut function. Ah, here. Let me check if I. Okay, let me just go back. Okay, so now I can. Now it works. Let me see. Let me see. It's run. Okay, now it works. So let me just. Okay, let me just redo Ctrl-Shift-Z. Cut QL 3 equals 3, and then I want to put here. Okay, it was wrong, because if E equal 100. Now it should work. Let me see. Understand? There is an error here, but I don't understand what is cut. Okay, cut QL. It looks maybe it's a double. Yeah, I think it is like that. If I equal 100 with 2 equal signs, let me see. Yes. So I think it is negative, and it is always negative. So let me try to put a value which is positive. So now I am removing this cut, because I think it is not needed anymore. And then it's QL. Let me just write this. QL1 I think it may work in this way. QL1 equal QL1 1. Let's try equal minus 0.5 and let's see what happens. No, it's still, it changed, but it's still eroding. So maybe that I have to put a positive value then.
Also, you have the time, then
let me see.
and then you verify.
Yeah, correct. But still, I was expecting to see, let me see if QL1 is 0.5, what happens? No, it doesn't change much. Okay, we need to just, I think we need to play with it and see what happens. Maybe that the right one, because I see a change. I see a change at the end. It is very high, effectively. Anyway, I think, unfortunately, I'm running out of time, and but we can play with it.